Alrighty, so this is Mr. Bell attempting to make a video over the Unit 3D notes packet, which is the one I gave you right before spring break. Hopefully you have it. If not, try to just follow along as best you can. The first lesson that we're going to go through is over something called L'Hopital's rule, which is going to go back and talk about limits, which I know we haven't done in a really long time, but hopefully you can remember it. Anyways, I want to review a little bit before we get into the new stuff of today. First of all, let's kind of look at the bottom, the three different ways that we can go through and answer any given limit question. We could do a limit graphically. That means from the graph. Those are really easy. Not going to talk about them very much. You can do the limit from the left, you can do the limit from the right, and you can check, hey, what's that overall limit? But remember that overall limit is only going to exist if the limit from the left and the limit from the right are approaching the same thing. We can also do limits numerically. That means from a table or just manually plugging in as my x values get closer and closer and closer to something, your target destination, you're looking for the corresponding pattern in the y values. Limits from a table, limits from a graph, pretty easy. Hopefully you can remember those from way back when. We spent most of our time and effort and energy and sadness doing limits this third way, which is analytically or algebraically. Using algebra or using some type of analytical skill, how do we answer a limit question? Now, we had a couple of different issues that we saw at the beginning of the year. Some of them we're going to kind of recap here, and then we'll get the new way called L'Hopital's rule, which is going to make our lives a whole lot easier. So let's recap this stuff at the top. Remember, for limits, when I'm evaluating, if I get a number on the top and a number on the bottom, well, that's going to be just fine and dandy. You're going to get a number, and then that's your answer. You're done. The issue is whenever we get an infinity or a zero coming up in one or both parts of the limit. So let's go through those situations, and then we'll get into the new stuff. If I get infinity over a number, when I go through and evaluate a limit, well, infinity divided by a number is just going to end up being infinity. That's an answer. It's a weird answer, but it's a perfectly good and acceptable answer. Or if I get a 0 divided by infinity, that's also really easy. 0 divided by anything is 0. So that's not a problem. Ever having a number in the denominator, you're always going to get an answer, no problem. Now the issue is, what happens when I get a number on the top and I get one of those weird things on the bottom? Well, let's go through them again. If your denominator gets really, really, really big, then the fraction overall is ensuingly going to get really, really, really small. So if you're evaluating a limit and you get something like a number over an infinity, it could be a plus or a minus infinity, doesn't matter. But if I get a number over an infinity with a limit, that answer is going to end up being 0. If the denominator gets big, the fraction overall gets really small. And in the other case, hey, what happens when I have a number and I get a 0 in the denominator? Now, I know you never want to divide by 0, but here, if we're working with a limit, remember that denominator never gets to 0. It's just really, really, really close to 0. And if that denominator gets really, really, really small, then the fraction as a whole is going to get really, really, really big. And this one could be a plus or a minus infinity. You would really have to pay attention to that ratio, whether it's a positive ratio or a negative ratio. But the general idea is if your denominator gets big, fraction overall gets small. Or if your fraction has a denominator that gets really, 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 really small, the fraction as a whole is going to get really big, either in a positive direction or in a negative direction. So anytime one of the layers, either the bottom or the top, anytime one of the two layers of a fraction ends up being a number, you're going to get an answer. But sometimes we hit these issues whenever I got a 0 on the top and on the bottom, or an infinity on the top and on the bottom. And if you remember way back when, we called those indeterminate limits, which means we cannot determine what the answer is going to be. So we had all these different techniques and strategies and algebraic manipulations that we could do to get the answer to these indeterminate limits. Remember, indeterminate doesn't mean there's not going to be a limit. Doesn't mean no limit exists. It means I don't know what the answer is. We have to do something extra. All right, so let's go through and let's kind of recap what those strategies, some of them would have been. And then L'Hopital's rule is going to be kind of the silver lining. It's going to kill all those indeterminate limits and make them all really, really easy. So let's get back into this notes and see what we can do. The first page we're not going to bother doing. You can use your calculator and plug it in, or if you really want to know the answer, just go look at my notes key online. But I don't want to bother doing them right now. Similarly, the third page, we're not going to bother doing just because it's not the most important example. Really what I want to make sure you guys get covered is the material on this second page, which is how do I evaluate some of these limits that are initially indeterminate, and then once we learn L'Hopital's rule, how does that rule help us get those answers a whole lot simpler? So let's go through and do some of these examples. Start at the top. So here we got limit x is approaching -1, and I've got this rational function 2x squared minus 2 over x plus 1. The first and most common technique that we had whenever we were trying to answer a limit was to try to factor and reduce. So here I think if we were to factor this limit, remember you still have limit, x is approaching -1, you could factor out a 2, certainly. And then you could also factor that numerator a little bit farther. Oh, come on, pencil, you can do it. So just factoring that thing as far as we can see that, hey, it looks like something's going to reduce. And of course, if you think it's something that's going to factor and reduce, well then there should be something that reduces. And out of those two chunks in the numerator, it's going to have to be the corresponding chunk that matches the denominator that had better reduce. Because if you think somehow like that's the thing that's going to cancel, well, it doesn't match, and then you would still get stuck. But luckily here, when we factor, we do see that that chunk in the numerator is going to reduce with that chunk in the denominator. If you were thinking about what that would cause in the resulting graph of this rational function, remember that would be a hole in the graph. The hole doesn't affect the limit. It certainly affects the graph, but only at that one point. But that point missing doesn't affect the limit as you get closer to that point. So factor and reduce, that was our first and most common algebraic strategy to get around those indeterminate forms. Here, if we factor and reduce, still left with this, and then once you've reduced it, you always eventually want to go through and evaluate. So once we've reduced it, now I can go through and I can change all my x's to -1s. And then we'll get the answer. Let's see, -1 minus -1 would be -2. 2 times -2 would be -4. So look at that, we got the first answer done. Algebraically, we could have gotten around that indeterminate issue by factoring and reducing. I guess I probably should have checked it. If you would have plugged in the -1 into your original fraction, if you plug a -1 to the top, and if you would have plugged in -1 to the bottom, you would have gotten 0 over 0. Remember that 0 over 0 doesn't mean no limit exists. It means it's indeterminate. I don't know what the answer is. The answer ended up being 4, but we had to do something to figure out what the answer was, and that first something that we did was factor and reduce. That wasn't the only strategy we had. Remember, we could combine fractions, we could factor and reduce, which we did. We could look at the big terms, figure out what goes to 0. We could look at the small terms. We could use the conjugate, which we're going to do on the third example. We even had some special trig limits for sine of x over x and 1 minus cosine x over x. All sorts of different algebraic ways to answer these indeterminate limits. But the nice thing is that L'Hopital's rule, the one really easy calculus rule, it's going to cover all of those different 7 or 8 different algebraic strategies we had earlier. So it's a really good rule, but for sure, factor and reduce, very easy. Hopefully you followed that first example. All right, let's go through and do the second one now. I have a limit to infinity. Remember, if you have a limit to infinity, you're going to find just the biggest term on the top and just the biggest term on the bottom. There's other ways to do it, but that's the way I kind of liked you to do it. Limit to infinity means find the single largest term in the numerator, and then you can ignore everything else. You find the single largest term in the denominator, and then you can ignore everything else. And then you can just work with those two terms, one on the top, one on the bottom, and then that's going to end up giving you the answer. Remember, infinity meant you found the biggest term on the top, biggest term on the bottom. If this would have been a limit as x was approaching 0, you would have done the opposite. You would have found the smallest term on the top, would have found the smallest term in the bottom, and then you worked with those smallest terms. So infinity was the biggest terms, the limits to 0 would have been the smallest terms. Of course, if you would have plugged it in, you're going to get infinity over infinity, which is indeterminate, right? Limit does not exist. Doesn't mean there's no answer, just means I don't initially know what this answer is going to be. But if I have a limit to infinity, find the biggest term on the top, biggest term on the bottom, we're going to be able to get this pretty quick. You have an x squared, which is now going to reduce. Then you have limit as x is going towards infinity of just 3 over 2. So your answer is going to be 3 over 2. If you know your horizontal asymptote rules, you could also answer that question really quickly, right? Limit as x is going towards infinity, that's asking what's the right-sided end behavior of this graph? Now, if you know you have your horizontal asymptote rules for your rational functions, hey, the degree on the top was 2, the degree on the bottom was 2, those match. So when the degrees match, all you do is look at the ratio of the coefficients. So you have, find the biggest term in the top, or you could have divided everything